In the last segment, we talked about how random sampling is based in probability, so we should probably take some time and talk about the basics of probability. By definition, probability is the likelihood of an outcome divided by all possible outcomes. Probabilities are given in decimals, but they're derived from proportions or fractions. And so if we have a fraction, we can convert that to a decimal just by dividing, and that's what a probability is. Percents are when you take a probability or a decimal and you multiply it by 100. So when getting a probability and converting it to a percent, we'll start with a fraction, which is called a proportion. We'll do the division. That'll give us a probability, which is a decimal. And then we can take that decimal and we can multiply it by 100, and that will give us a percent. So make sure you know what probabilities are, what proportions are, and what percents are. So let's go ahead and go through a couple of examples. So let's say I had a coin, and on this coin I wanted to flip it, and I wanted to get heads, and so I wanted to know what's the probability of getting heads. And so if I have a coin, it has two sides, so therefore it has two possible outcomes, either heads or tails. Now the side that I want, the specific outcome, is heads, and there's only one side with heads. And so the proportion of getting heads on a coin is 1 over 2. If I divide it, I can get the probability of getting heads, so 1 divided by 2, and that gives me a probability of 0.50. Same thing with rolling a die, that if I wanted to roll a 1 on a 6-sided die, the specific outcome I'm looking for is a 1. All possible outcomes are all 6 sides of the dice, and so therefore my proportion is 1 over 6. I do the division, and I get a probability of 0.1666 repeated. I can round it to 0.17. If I wanted to, I could convert that to a percent just by multiplying it, and I get about 17%. Now for the purposes of this course, we're not going to make probabilities too difficult, but we will add a little bit more to what we've just previously learned. So in particular, let's talk about and or statements. Now these statements tell us about certain mathematical operations. So if I say or, and so let's say I want to know the probability of something happening or another event happening, then typically that's going to tell me I'm going to be adding probabilities together. Now if I have an and statement, the and will tell me that I'm probably going to be multiplying my probabilities together. So let's say I wanted to know the probability of rolling a 1 or a 3 on a 6-sided die. Now rolling a 1, the proportion would be a specific event of rolling a 1 over the 6 sides of the die, in other words 1/6. The proportion for rolling a 3 would be the same. There's only 1 3 on a 6-sided die. There is overall 6 sides, and so the specific outcome is still 1, and all possible outcomes is still 6. And so I have a proportion of 1/6 plus another proportion of 1/6, and so I add those together, I get a proportion of 2/6. And so if I was to turn that into a probability, I would take 2 and divide by 6, and that would give me a probability of 0.33. So we would do a similar calculation if we were wanting to get the probability of picking a face card out of a deck of cards. So in a deck there are 52 cards. Also in a deck there are 3 face cards. There's jacks, there's queens, and then there's kings. The jack, queen, and king occur 4 times each in a deck. And so we can look at each one of those particular outcomes, whether it's a jack, queen, or king, and we can create a proportion for each one. And so for a jack, there's 4 jacks in a deck of cards, and there's 52 cards in a deck, so we can say 4 over 52. Same thing with queens, there's 4 queens in a deck, so we'll say the proportion is 4 over 52. The same thing for kings, so the proportion would be 4 over 52 as well. And so here we're picking a face card. In other words, we're saying if I was to pick a card from a deck of 52, what's the probability of getting a jack, or a queen, or a king, and we can end up with an overall proportion of 12 over 52. And so I can convert that to a probability by taking 12 and divide by 52, and I get about a probability of 0.23. Now I can take that one step further and turn it into a percent. And so if I multiplied that probability by 100, I could say there's a 23% chance that I would pick a jack or a queen or a king if I was to pick one card from a deck of 52 cards. Now let's go ahead and talk about the AND statement. So the AND statement tells us we're likely going to be multiplying our probabilities together. So let's say we want to know the probability of getting a boy and then a girl into subsequent pregnancies. And we're going to make a couple of assumptions here. The first is that we're having only single birth pregnancies and not multiple birth pregnancies. The other assumption is that there are only two outcomes, boy and girl, but we know that that's not always the case. So we'll make those two particular assumptions, that gender is not ambiguous and that we only have single pregnancies or single births and not multiple births. Okay, so if that's the case, then the probability of getting a boy in any one pregnancy is 1 over 2. So boy would be our specific outcome, and all possible outcomes would either be boy and a girl. So we have a proportion of 1 over 2. And then for the next pregnancy, the proportion would be the same because a girl will be one of two possible outcomes, either a boy or a girl, and so that would be 1 over 2 as well. So we could then multiply those two proportions together, and that would give us the probability of getting a boy and then a girl into pregnancy. So we'll take 1/2 times 1/2, that equals 1/4. We then do the division, 1 divided by 4, and that would give us a probability of 0.25. And again, we could turn that into a percent by multiplying by 100, and we could say there's a 25% chance of getting a boy and then a girl into pregnancies. So we can do the same thing if we're rolling dice. So if we want to get the probability of rolling a 1 3 times in a row, we'll take the proportion for rolling a 1, which would be a 1 over the 6 sides of the dice, so 1/6, and we'll multiply it by 1/6, and then again by 1/6 because we're rolling the die 3 times, and so we multiply those 3 together, and we end up with a probability of 0.0046. And so in other words, if we were to change that to a percent, that the percent chance of rolling a 1 3 times in a row would be 0.46 of 1%. So not only should we talk about AND and OR statements, we should also talk about independent and dependent trials. And if you remember back from the second day of lecture, we had an activity where you picked a door, and behind one of the doors was an extra credit point. And in that exercise, we talked about independent and dependent trials. And so with independent trials, the probabilities do not change. And that's because the current trial is not dependent upon any previous trial. So examples of this might be coins, dice, births of children, etc. And so every time I flip a coin, and let's say I wanted to get heads, the probability of getting heads would be 0.5. And so if I was to flip a coin, and let's say I got heads, if I was to flip that coin again, the probability would still be 0.5. If I was to flip a coin 5 times in a row and get heads every single time, the sixth trial, the probability would still be 0.5. It wouldn't change because each time I flip the coin, the trial is independent of what occurred in the previous trials. So it didn't matter what happened before, the current trial probability is still 0.5. Now with dependent trials, the probabilities change. And so with dependent trials, it depends on what occurred beforehand. And so what occurs beforehand affects our results of what we're currently doing. And this is the world where we live, where all the events that take place are dependent upon previous events. And so probabilities are always constantly changing, they're varying. So anyway, so some examples of dependent trials might be playing cards without replacements. So maybe I have a deck of 52 cards, and I want to know the probability of pulling a face card. And so as we talked about earlier, the probability of pulling a face card is 0.23. The proportion is 12 cards out of a deck of 52 cards. So let's say I pull a card out of this deck, and it is not a face card. So if I don't put that card back into the deck, I now only have 51 cards in the deck. But there's still 12 face cards in the deck. And so the proportion now is 12 over 51. And so the probability, if I was to turn that into a decimal, would be 0.24. So the probability on this second trial has increased from 0.23 to 0.24. And so the probability has now changed. and that's because I didn't put that card back in the deck. It became a dependent trial. So another example might be pulling names from a hat, again without replacement. So I might have 10 names in a hat, and I want to know the probability of pulling out Sarah's name out of these 10 pieces of paper in a hat with names on them. And so I pull out a piece of paper, and on that piece of paper, the name is Matthew. So the probability of pulling Sarah was 0.10. In other words, 10%. The proportion was 1 over 10. But I didn't pull out Sarah's name, and so I don't put Matt's back in. I just discard Matt's name, and then I reach back into the hat and I pull another piece of paper out, and maybe I get Corey. So that second event, that second trial, the probability of getting Sarah's name was 1 over 9, because Sarah was still in the hat, but there was only 9 names left in the hat. And so the probability increased from 0.10 to 0.11, and in this second trial, I still didn't get her particular name. And so I could then again reach back into the hat, and so the probability now, because I'm not replacing names, is now 1 over 8 names, because there's 8 names left in the hat, and so the probability increases again. And so with dependent trials, the probabilities are changing depending on the events that happen beforehand. So why do we care about probability? Well, as we already talked about, samples themselves are probabilistic. They're based in probability. That when we select a sample, even randomly from the population, there's a chance that that sample does not represent the population, because we left it up to chance, we left it up to probability. And so if we're inferring from our samples to the population, then we need to know at what level of probability we can make this inference, or that we can say the results of our samples applies to the larger population. Now, not only are samples probabilistic, but statistical tests are also probabilistic. And so we're going to learn about several statistical tests this semester, and each one of them are based in probability. There's a certain underlying chance that is related to each of those tests. So we have to remember that if it's based in probability, our results are not going to be exact, but rather to a degree of confidence. So whenever we get a result from a statistical test, we have to realize that underlying those results is chance, or is probability. And so we have to realize that there's always a chance that our results are not correct, or they're not accurate. And that's why we really care about probability when it comes to statistics. Now in Module 2, you'll remember that when we got a normal distribution and we applied percents to that distribution, we created a probability distribution. So in other words, we can treat the population as if it's like a pair of dice. So with any given region underneath our distribution, there is a certain level of probability. So for example, if I wanted to know the probability of selecting someone from the population randomly, and I want to know the probability that they were an average person within that population, then there would be a certain probability between a z-score of -1 and a z-score of 1, or what we would categorize as normal. And so if we look at our distribution, the probability between 0 and -1z is 0.34, and the probability between 0 and 1z is also 0.34. So notice here we take those percents and we turn them into probabilities by dividing by 100. And so if I add those two regions together, I get 0.68. And so there's a 0.68 probability that any one person I pick from the overall population would be categorized as normal. So again, as a probability, 0.68, we can turn that to a percent. We can say there's a 68% chance that any one person we randomly select from a population will be categorized as normal. And so that's how we're going to use probability in this course. We're always going to refer back to the normal distribution and how it relates to probability, and in particular probability of selecting individuals or selecting samples from the overall population. So you should be able to take what we've learned with probability and be able to answer questions, and or statement questions about the probability of selecting individuals from the normal distribution or from certain categories underneath the distribution.